In this video, I want to talk about multi-loop circuits, and I'll just, in a few moments, I'll explain what multi-loop circuits are, and we'll see how it extends the idea of voltage dividers and helps us to see some new things about them. So in the previous videos, we looked at voltage dividers, like the one that you have on the screen. So in this voltage divider, you have a voltage source here, which is uh, has a potential of V, and this is the positive end of the voltage supply, and this is the negative end. And there are two resistors. Let's assume that their resistances are equal. So this is R, and this is R, and we take the output voltage at this point. Okay, so the output voltage is taken across this resistor R. So in that case, what will be the output voltage in terms of the input voltage? I'll leave you to work it out, but I'll just give you the answer. It's going to be V output is going to be V over 2. And the reason why it is V over 2 and there is no term depending on R is because both these resistors are equal. So this circuit is able to divide the voltage by a factor of 2. Okay, so in one sense you could write this circuit like this, right? So you could think of it as a black box, and this is a divider circuit, and this divider circuit takes an input voltage V with respect to, of course, a particular input. So it takes V and it gives us an output VO, which is equal to V over 2. Okay, so now consider this circuit. This is made up of two blocks, two divider blocks. Okay, each of the divider blocks divides the input voltage by a factor of 2. So the output at the first block is going to be the output here. Let's call it V1 is going to be V over 2. Okay, and this divider blocks divides the input to it, which is V1, into makes it half. Okay, so we get V, let's call it V2 is equal to V1 over 2, which is equal to V over 4. Okay, ideally if we put two divider blocks, what we expect is both of them, they divide the voltage by half each, and so the total voltage is going to be divided by 4 times. Fairly straightforward, right? But in reality that does not happen, and we want to discover why it does not happen. And in the process, we'll understand something about resistive circuits a little bit more and understand how we can interface two circuits and what are the issues associated with it. So that's where we are going. So what I'm going to do is I'm going to replace each of these circuits with the resistor voltage divider circuit that we studied before. And let's see how it functions. So here's the circuit, and what I've done is I have drawn in blue the first voltage divider circuit, and I've drawn in black the second voltage divider circuit. And let's see how this works. Now, first of all, what I want to talk about is that this is an example of a multi-loop circuit. What do I mean by that? Now, if you look at how the current travels from this voltage source, so the current is going to travel through this resistance, and then there are two paths that the current could take. One is through this resistance and back to the voltage source. So that is one path for the circuit, or one loop for the circuit. Another current, the current then could either flow, of course, through this resistance, or it could flow through this resistor, right? So the current could go like this through this resistor. It can go through this resistor and then back and back into the power supply. So can you see that there are two paths for the current to return to the power supply? and therefore this circuit has two loops in it, and therefore this is called a multi-loop circuit. Okay, so let's now take a look as to how this circuit works. So let's so this is the power supply signs, and the current is going to move like this. Let's call this current I, and once it comes to this point, the current is going to divide into two parts. One part goes like this, let's call it I2, and another part goes like this, let's call it I1. Now all this current I2 is also going to flow through this resistance, because the current here is going to be zero, because this is an open circuit and you can't have current. Imagine charge is flowing here, and if there is no path for the charge to go out of this point, if there is a current flowing, then charge will be accumulated here. Now we know that that cannot happen, because if the charge is accumulated, then that is going to resist the flow of current. So currents can only flow in closed loops, and this is not a closed loop, therefore no current can flow. So all the current that flows through here, which is I2, is also going to flow through this resistor. So this is going to be I2. Okay, so one of the equations that you can write just looking at this point is that this current I equal to I1 plus I2. Now the aim that we are trying to get at, our aim in doing all this, is to find a relationship between the voltages, or we want to find this V output, and therefore we are writing all these equations. So let's just think about this one thing here. So let's start with this point and call this point A. What will be the voltage of point B with respect to A? So what is the difference in the voltage between point B and A? So you could easily see that VBA equal to V, right? Because that's the only voltage that there is in between here. So if I say what is the voltage of point B with respect to A, the difference is there because of this voltage source. So VBA is equal to V. So similarly, let's call this point C, and I say what's the voltage of point C with respect to A. So I want to find out the voltage of point C in relation to point A. And how would I do that? I could break this up into two parts, and I could say, well, VCA is going to be equal to VCB plus VBA, right? So it's the voltage difference across this resistor and the voltage difference across this source. So if you add both of them up, you get the voltage difference across point C and A. Now we know what VBA is already. What is VCB? Now if you look at this resistance, there's a current flowing through in this direction, and so the voltage across this resistance is going to be, so this is going to be the positive end, this is going to be the negative end, because voltage drops across the resistance. And what is the voltage drop going to be across this resistance? It is going to be I, which is the current, times the resistance, IR, according to the Ohm's law, right? So what is VCB going to be? VC, the point C, is at a lower potential than point B, right? So therefore we can write VCB will be equal to minus IR, and VBA is of course V, so IR plus V. So that is VCA. Okay, now let's think about what is the potential D of point D with respect to A. And again, what we can write it as is, we can write it as a sum of this potential VBA added to the potential VCB added to the potential VDC. Okay, so let's just write that down. So we have VDA equal to VDC plus VCB plus VBA. And what is that going to be? So we know these two potentials, VCB and VBA. What we don't know is this VDC. And what is this VDC going to be? Again, notice that what we have is that there's a current flowing in this direction. So this is going to be the positive end. This is going to be the negative end of the resistor. So this point is going to be at a higher potential than this point. And what is going to be the potential difference? It's going to be I1, which is the current flowing, times the resistance R, right? So what the potential VDC is going to be? Minus I1R plus VCB is going to be minus IR plus VBA is of course V. So that is VDA. But notice that this point D is the same as point A, right? Why is that? Because in the circuit, they're just connected by a wire. There's no component in between. So these are actually equipotential points. So in a sense, there is no difference between the voltage of A and D. So VDA is actually 0. But we have already written an equation for VDA, which is this. So this sum has to be 0. So let's just write that down. So 0, but this is equal to minus I1R minus IR plus V. So this thing that we have derived here, let's just think about what we have done here. What we have done is we have taken the sum of the voltages across each of the components in a particular loop, and we have found that the sum of the voltages is equal to 0. Okay, and this is called the Kirchhoff's voltage law. It's a very famous law that we use again and again in electronics. And the Kirchhoff's voltage law basically states that if you add up the voltages across all the components in a particular loop, the voltage is equal to 0. And the basic idea of the Kirchhoff's voltage law is that if you go through a loop completely, you return to the same point. So therefore, when you add up all the voltages, it has to sum up to 0. Okay, so let's just apply this idea of Kirchhoff's voltage law for the second loop, which consists of this voltage source, this resistance here, and this resistance, and then we reach the same point. Okay, so what we're going to do is we're going to write the sum of the voltages in loop 2. We call that loop 2, right? So the first component here is this component. And what's the voltage here? The voltage is increasing here by a value of V. So we have V, and then the second component that we have in the loop is this resistance, but the voltage is dropping here. So the voltage is higher at this point than at this point, because when a current passes through a resistor, the voltage drops. And what is the amount of voltage drop? It's going to be I times R. So we write minus IR. And then we have this other resistor. Again, the voltage drops across it. What's the current flowing through it? I2. The resistance is R. So the drop is going to be minus I2 times R. And similarly, if you look at this resistance, again, the drop is going to be I2 times R. And so we can write again minus I2 times R. And if we do that, what we have done is we have reached the same point. We have reached the point that we started out with, or we have reached the end of the loop, and therefore we'll have all of this entire equation will be equal to 0. So that's the Kirchhoff's voltage law as applied to this outer loop here, which we were calling loop 2. Okay, so now we have three equations, right? So you have one equation here, you have one equation here, and you have the third equation here. Now, using these three equations, there are three variables in these equations, unknowns, I2, and I1. And using these three equations, you should be able to uh, get the values of each of these values. We already know what is V and what is R. Okay, so let me just write the equations out in the next slide and let's solve it. So we have these three equations, and if we solve these three equations, what we get is we get I1 equal to 2 over 5 V over R, and then we get I2 equal to 1 over 5 V over R. Okay, so we have this circuit and we have already calculated the values of I1 and I2. And what we actually need is the value of the output V naught, which is VO, which is this output, right? So if you look at this voltage, this is the voltage across the resistance R here, right? And I'm sorry, I've just forgotten to put the values of the resistances, and all the resistances were R. So let's just write it. So across this resistance R here, whatever the voltage drop across this R is the output voltage. So what's the output voltage going to be? So VO is equal to I2 times R, and we have already calculated I2 as V over 5R. So just multiply that with R. So we get the output as V over 5. And now you can see that putting together two voltage dividers, each of these voltage dividers was, so this blue resistors are one of the voltage dividers. They were supposed to do a voltage division of half, and this voltage divider was supposed to do another half, so the output was supposed to be 1/4 the input voltage, but now we have got 1/5 of the input voltage. Probably it would be interesting to find out what the output of this first set of resistors would be. So what would be the output at this point? So what would be the voltage at this place? Right, and this we can, let's call it V1, and of course V1 is equal to I1R, so we could write V1 equal to I1 times R, and I1 we know is 2V over 5R, and that times R, so we get 2V over 5. So what we were expecting to get here was V over 2, but instead we get 2V over 5, and at the final output we were expecting V over 4, but we get V over 5. So something has, so when we are putting these two circuits together, the second circuit is somehow influencing the first circuit so that its output is no longer V over 2. and the putting together of the two circuits is influencing each other. Let's see why this happens. So let's look at this circuit once more. And what I've done is I've just put a break in the wires here and here, so that now this circuit is acting independent of this circuit. Okay, so now just think about this. What is the current that is flowing from here? It's the current I, and all of this current is now flowing down through this resistance as well. So the current that is flowing through this resistance is the same as the current flowing through this resistance. And if that is true, at the output you get a voltage of V over 2. But when you make this connection, and let me just make it with a different color. When you make this connection, the current that is flowing through this resistance is not all of it flowing through this resistance, because we have connected this circuit here, right? So some of the current is flowing like this. So I2 is flowing like this, while only I1 is flowing through this resistance. And therefore, this circuit has changed the current that is flowing through this resistance, and therefore the voltage at this point, and therefore the voltage at this point. Right? So circuit 2, and let's call, so this thing is circuit 2. So circuit 2 has somehow influenced, and we have just seen the mechanism of influence. We've seen it has influenced circuit 1, basically by changing the amount of current that flows through this resistance. And this is a problem that in electrical terms is called loading. Loading is the phenomenon of a circuit that is connected to the first circuit changing the output of the first circuit, right? So circuit 2 changes the behavior of circuit 1, or in other words, circuit 2 is loading circuit 1, and therefore circuit 1 does not behave as it would if it had been an independent circuit. So let's summarize what we learned in this lecture. Some of the things that we learned were, one of the things was, what are loops? So loops are basically closed paths for the current to flow in a circuit. And then we looked at the Kirchhoff's voltage law, which basically stated that the voltage, the sum of the voltage across all the components in a particular loop would be 0. Okay. And then we looked at the concept of loading, the idea being that if you put two circuits together, each of the circuit can somehow influence the output of the other circuit, and they may not behave as if they would when they were independent of each other. And that is the idea of loading. We have also looked at the Kirchhoff's current law, though I have not really mentioned it as such. The Kirchhoff's current law is the idea that current cannot be either produced or destroyed in a circuit, right? So if you have a very in our circuit we had a resistor combination like this, and I'm not drawing the complete circuit, there is some circuit on all these sides. So if a current is flowing like this, it divides equally into I1 and I2 in these parts, and we can write I equal to I1 plus I2. So at any point, the currents that are flowing into the point would be the same as the currents that are going out. So that's Kirchhoff's current law.